JD,
Yes, yes.
so which road are you taking when you're going home?
So today when I'm going home, the road that I'm going to take or the road that I'm going to use from here where I work to where I stay, I'm going to use the road that minimizes my action. In other words, that makes the action stationary. Let me try to show you what I'm trying to explain here on the board. Assume that this is the point where I work, right? And this is where I stay. Let's call where I work. Okay, so let's say where I work is P1 and where I stay it's the second point, it's P2. So your question is which route or which road am I going to use when I'm going home? Remember, I'm a mathematician. Like I said, the road that I'm going to take or the route that I'm going to take is the one that makes my action stationary. What do I mean by that? Because there are so many ways in which I can take as I'm going home. Either I can take this route, let me call maybe that route alpha, or maybe I can take this route, let me call that route maybe beta, or maybe I can take this route, let me call that route gamma, or maybe I can take this route, let me call that route maybe delta, or maybe I can take this route, let me call that route maybe epsilon. Well, so I can see that there are so many routes that I can take as I go home. But by the end of the day, I need to make sure that I take the one, right, that makes my action stationary. What do I mean by that? So generally speaking, in a layman's perspective, remember you have to look at the route that minimizes the time, that minimizes the fuel, that minimizes the risks. There are a lot of things that you have to look at. So although I'm going to explain this in a complicated but a very interesting way that you can apply in any particular given situation, whether it's in economics, whether it's in engineering, etc. So what am I trying to say here? So imagine I'm looking for the integral of x of t, right, which is equivalent to the integral of what? From P1 to P2 of the Lagrangian function, right? This Lagrangian function is expressed in terms of time, in terms of position, right, as well as in terms of velocity. Right. So what do I mean by the Lagrangian function? So remember, the Lagrangian function, which is denoted by a letter L, is basically the discrepancy between the kinetic energy, which I can denote by letter T, and the potential energy. Remember, T, which is the kinetic energy, it tells us more about the energy that a particle possesses, right, while it is in motion. So its velocity will tell us more about its kinetic energy. What about potential energy? This is the energy possessed by a particle due to its position in the gravitational field. So yes, the Lagrangian function is the difference between the kinetic energy and the potential energy. So let's say I've got this Lagrangian function where which is expressed in terms of time, in terms of position, in terms of velocity. The reason why I use the subscript I here, it depends in the manner in which I'm going to use when I'm traveling. Either I'm going to travel in a straight line in 1D, or I'm going to travel in a 2-dimension, or I'm going to travel probably in a 3-dimension, etc. So my I is equivalent to 1, 2, 3, all the way up to n. All right, let's say this equation is subjected to certain constraints. Let's say maybe it's subjected to P, auxiliary conditions. Let's take, for instance, we've got G subscript mu, which is also expressed in terms of T, Xi, as well as Xi bar. So this is time, position, and velocity, and is equal to 0. So in this case, my mu is going to be equivalent to 1, 2, blah 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 blah, but all the way up to P, where this P should be less than n, right? But there's also another way in which these auxiliary equations can also be, or conditions can also be provided. I'm going to explain that maybe in another video where you might be given what are called mere equations. So let's take, for example, instead of them giving you the conditions in this form, they might also give you the conditions in the form of an integral. Let's say from P1 to P2 times the integral of L of mu expressed in terms of time, position, as well as velocity, and then they said is equivalent to L of u. But I will explain this later because this is part of what are called the mere equations. Okay, so let's say you've got these auxiliary conditions. Then what? Then our new Lagrangian function, which I can denote by lambda, expressed in terms of time, in terms of position, as well as in terms of velocity. But also we also have got lambda, which are Lagrange multipliers. Let's call that lambda mu. So this is equivalent to what? How do I simplify this? So this is equivalent to lambda, which is expressed in terms of time, position, as well as velocity, right? Plus the summation of what? The summation of lambda mu times g mu, which is expressed also in terms of time, position, as well as displacement, right? So this is mu starts from mu is equivalent to 1 all the way to mu is equal to p. But remember the condition that p should always be less than 1. Okay, so once we have this kind of a situation, we remember, like I said, we are trying to optimize here, to take the extremal value. So in this case, the extremal value occurs when this thing is equivalent to 0, when the del of lambda is 0. So if the del of lambda is equivalent to 0, then what about this one, right? So this one, we know that this will give us the partial derivative, this will give us the derivative, right, with respect to t of what? Of the partial derivative of the Lagrangian function with respect to velocity, right? Minus the partial derivative of that same Lagrangian function, but with respect to position now, right? Plus, what about this one? So for this one, we take the summation of what? So in this particular case, we take the summation of lambda mu, right, times, so here let me open the brackets. We then take the derivative with respect to t of what? Of the partial derivative of this g subscript mu with respect to what? To velocity, right? Minus the partial of g mu, right, with respect to position, right? And then we also have to add with the partial derivative of g mu with respect to velocity times the derivative of lambda mu with respect to t, right? Let me close the brackets in this particular case. So this summation starts from all the point from lambda, from mu1 to p. So can you see the expression that we ended up with? So it depends if you are given probably two auxiliary equations, you ended up obviously with lambda 1 and lambda 2 etc. But what if the auxiliary conditions are not provided in this way? What if they are provided in this form, in the form of an integral? We call those mere equations. How do we handle that such kind of a situation? So if we are given the conditions in this form, then you may realize that the derivative with respect to t of the partial derivative of the Lagrangian function with respect to position, right, minus the partial derivative of that Lagrangian function with respect to position. This one was with respect to velocity. Remember, there is a prime here. Take note of the notation so that you won't get confused. Here we said minus the summation from mu equals to 1 up to p of what? Of lambda mu times the derivative with respect to t. But here, according to Mayer equations, I can't deduce for now, but I can just show you immediate results. So obviously, if the conditions are given in this kind of a format, here we are taking the partial derivative of L mu with respect to velocity, right? Minus the partial derivative of L mu with respect to position, right? Plus, right? Plus what? Plus the partial derivative of L mu with respect to velocity times the derivative of lambda mu with respect to t. Right, so these are the final results. We call this the extended Lagrangian function, and this one is also the extended Lagrangian function, but which tends to involve what are called the Mayer equations. So if I work out this, either this kind of a Lagrangian function or this kind of a Lagrangian function, by the end of the day, I will deduce my path, which is going to be xi of t. So by the end of the day, I'll choose which path by the end of the day do I take. Some of you might think, okay, you can take the shortest distance. It's not about taking the shortest distance. The idea is that path makes the action stationary, right? That's the most important part. So if you solve either this equation or this equation, you can get the path. And this what always comes in my mind whenever I think of going home, that okay, for me to be at where I stay from where I work, which path do I have to take? Every time I think about that, I always think about this Hamilton principle, which was also backed by the Euler Lagrange equations and also spiced with Mayer equations. So it's not just about going home, like I said. You know, even if a particular country decides to strike another country, you know, there are a lot of calculations that they have to do if they want to know that, okay, this ballistic missile or it's a cruise missile that they are launching. Imagine if the president of South Africa is thinking of attacking the president of Zimbabwe. Obviously, scientists, they have to play a crucial role in calculating, in playing around with the calculations so that their ballistic missiles can hit the right target of a particular country. So, yes, but besides that, there are so many applications where the Euler Lagrange equations can be used. Awesome. Hopefully you understand your questions of the path that I'm going to take when I'm going home.